All right, perfect. Let's go ahead and get started. So good morning, everyone, or good afternoon, depending on what time zone you are in. Thank you so much for joining us for the QChem webinar about to be presented by Juan. We're really excited to have him here. First, a little bit of an introduction. Juan Arias Martinez got his PhD in chemistry from UC Berkeley in 2023. He worked in Professor Martin Head-Gordon's group using orbital-optimized SCF references as a starting point for accurate computational modeling of X-ray absorption spectroscopy. He then, as his thesis work, developed a model that was capable of predicting the X-ray absorption spectroscopy signatures of excited states that are sought after in femtosecond time-resolved X-ray absorption spectroscopy experiments. So after he wrapped up that work in 2023, he moved on to Sandia National Labs, where he is currently working in Dr. Laura McCaslin's group on designing new optoelectronic materials based on organic donor-acceptor charge transfer complexes. And he, in fact, recently contributed one of the main features in QChem 6.4 of delta SCF for also modeling excited states and spectroscopy and stuff like that. It's a really nice alternative to TTDFT. And I'll let him tell you a little bit more about his work with that, making a more streamlined user interface, and then also how he's been applying that in his work over at Sandia. So without any further ado, we're really excited to have you here today, Juan. And I will go ahead and hand this over to you. Oh, quick note before you get started, sorry. I should mention, if you have, to folks in the audience, if you have any questions as he's going through his talk, please feel free to post those in the chat or the Q&A section, and we will have a Q&A session at the very end of his talk. So thank you so much. Sorry about that. Go ahead and share your screen.
No worries. Thank you, Shannon.
Thank you.
Hopefully the screen works and everyone hears me okay.
I can hear and see everything perfectly fine, so thank you.
Wonderful. Then thank you for having me, Shannon, and to the whole QChem team. And thank you everyone for being here. I am genuinely excited to share with you about some of the improvements that I've made in the OO-DFT user interface in QChem. This is a project that was sort of born out of necessity. I run these sort of calculations in my own research, and we're gonna get to see why they are a little bit difficult to work with, even though they're extremely accurate, and some of the work that I've done to alleviate that problem. We're gonna begin with just speaking about orbital-optimized DFT in general, talk about how it performs for charge transfer excitations, and briefly go over some of the recent advances that have taken place in the general electronic structure community that is interested in this. We'll move on to the new Delta SCF driver, and wrap up the talk with how I'm using this driver in my own research at Sandia National Labs. So the broad strokes of OO-DFT is that the SCF energy, or rather the SCF equations, don't have only one solution. Usually we're interested in targeting the ground state, which would be the global minimum in this sort of hyperdimensional surface that is defined by the orbital degrees of freedom. But it turns out that there's other solutions, and these other solutions, these other stationary points, they correspond to excited states. And this sort of idea has been floating around since the 70s. But there's sort of been recent theory-based work to sort of understand the fundamentals as to why this actually works in practice. And when you do these sort of calculations, you usually begin with the ground state. You get an energy and some Kohn-Sham orbitals. Then you generate an excited configuration that resembles the state that you have in mind. And then you allow the orbitals to relax. That gives you a different energy and a different set of orbitals that then you can use to compute excitation energies and any sort of property that you're interested in. So if you're trying to get an absorption spectrum, you would, for example, be interested in the transition dipoles and the oscillator strength. And these sort of methods, this slide should have been before. This is sort of pictorially what it looks like. I did a lot of work in coarse spectroscopy during my PhD, so we'll be seeing this example of water with some frequency. So yeah, you just get your sort of Aufbau configuration for water with your ground state calculation, and in this particular case, we're interested in a core excitation where we're promoting this 1s electron into the 3s. And then we use specialized solvers to try to hold on to that configuration and then relax the orbitals. And hopefully you can see that the 3s orbitals has contracted a little bit as a response to the charge migration. So yeah, this is sort of how it looks like in practice. And it turns out that OO-DFT is really, really good. I mean, it's almost too good to be true sometimes. Once again, going for core spectroscopies, there's a bunch of numbers here, but what I really want to highlight here is that OO-DFT does better than equational motion coupled cluster singles and doubles for core excitations. And I mean, that's just spectacular. You know, we're talking about an ON to the 6th theory here, and we're beating it with basically mean field cost. Yeah, this is really good. And same situation holds for different kinds of CT states. There's been some benchmarks recently for intramolecular CT states, which basically migrate charge from a single molecule from one side of it to the other. So say this lone pair and beta dipeptide, migrating this lone pair electron into the pi star system that is in the carbonyl at the other end of the molecules. I did a sort of a small test of my own when I was preparing this presentation, and same situation repeats itself with a decent modern functional. We're getting energies that better match CCSD-T than CCSD. Similar situation happens for intermolecular CT states, where now we're migrating charge from one molecule to a different one. So Miko Labogo and Christopher Stein will tell you that delta CF outperforms TD-DFT for intermolecular CT states, and it has been known for quite some time at this point that TD-DFT suffers for these particular kind of excited states for a variety of different reasons. So delta CF, yeah, delta CF does it for you. So what's the catch here? It's really good, but delta CF is, or just orbital-optimized DFT in general, is difficult to work with. I have sort of a love-hate relationship with it because, as we're just seeing, it gives spectacular numbers, but it is just in practice painful to work with. And don't take it from me, take it from the many users that use these kind of theories. And that has a variety of different reasons. One of them has to do with the fact that just the sort of underlying electronic structure is more challenging for OO-DFT than it is for the ground state. And maybe it's a good point to sort of start being a little bit more specific about what we mean when we say OO-DFT. I like the term because it's sort of like in the name, it encodes what it means. It's just you're optimizing the orbitals for a specific excited state. But there's sort of a variety of different flavors of OO-DFT that exist. And you know, they're all related in some ways, and sometimes they have like small differences, sometimes they have large differences, but they all fall under this general idea of optimizing orbitals for a specific state. The ones that I'll be talking about are delta CF, which is arguably one of the most well-known and most used OO-DFT methods, which is a single determinant method that is applicable to high-spin states. And I'll also be talking about ROKS, which is effectively a two-determinant method that is applicable to open shell singlets. Yeah, so as we're talking about, the electronic structure is more challenging for this sort of states, and you need specialized solvers that are able to land you on the settle points that you're trying to target. because the majority of solvers out there are designed for the ground state. They're minimizers, but this time we're trying to land in settlements. So QChem features a variety of them. MOM and its variants are amongst the most sort of well-known and well-used solvers, but there's others, of course. And yeah, so it seems to me that in the past few years, let's say 5 or 6, there has been sort of an avalanche of papers that talk about OO-DFT and sort of investigate the fundamental theory behind it, or try to come up with new, better solvers, incorporate solvation, try to extract chemical information from the wave functions themselves or the densities. Being able to use this method in dynamics, benchmarking, changing the initial guesses, making this applicable for crystals. Truly, there has been a large growing interest in OO-DFT, and the reason is because it does really good. And sort of we want to push this method forward so that we can do new science with it. But I dare say that one of the challenges that also hinders OO-DFT from its full potential is truly just the user interface. Like, the advancements in electronic structure are important, they're essential. Without them, we're not going to move forward. But we also need for these calculations to be easy to carry out. And this is what I'm going to be talking to you about today. And yeah, it's sort of like computational ergonomics improvements that I hope makes these sort of calculations easier for the average user that is just trying to compute the spectrum of a molecule that they're interested on experimentally, and to the expert computational chemist alike that is perhaps interested in doing benchmarks or doing high throughput calculations. So without further ado, let's talk about the new driver. Basically, just allows us to tell QChem exactly what we want to do in an easier way, and it automatically outputs quantities that are relevant, that perhaps before you have to go fish for in some way. Step number 1 is going to be to tell the driver what excited state we're interested on. So let's go back to beta dipeptide. We are interested on, in this particular case, in the lone pair to pi star transition. So we go and take a look at the canonical orbitals, and they look something like this, where just orbital number 39 is indeed that lone pair, and orbital 40 sort of resembles the pi star system that we're interested on. They happen to be the HOMO and the LUMO. So step number 1 is going to be to tell the delta SCF driver that we want, open shell orbital to be this one, HOMO, and the other one to be this one, the LUMO. Alternatively, we can use TD-DFT states as a guess, and we'll talk more about that in a second. Next step is going to be to tell the driver what kind of calculation we want to do. So something nice about this is that we can run sort of different multiplicities associated with the same orbitals in just one single input. So just always using the closed shell reference as sort of the pairing configuration. In this case, we're asking the driver to carry out a single calculation, a doublet, and a triplet, and they're all going to be restricted. So for the doublet and the triplet, we will be able to use just standard restricted open shell SCF theory, which is what people often refer to as delta SCF. This is so this for high spin states, it's okay to just use a single determinant. Things get a little bit more complicated when we're trying to describe singlet excited states, because when we're talking about open shell singlets, we need multiple configurations. So this is precisely what ROKS is. I myself, I'm a fan of restricted. I don't like unrestricted personally, but perhaps you do. So you can also run unrestricted calculations if you so desire. Same thing for the doublet and triplet, but once again, for the singlet, it then gets a little bit more, it's different because you cannot really have an unrestricted singlet with one determinant. At that point, what you have is sort of a mixed state that is halfway in between the triplet and the singlet. It doesn't have an S square of 0 with it, which is what we're looking for in a singlet. But something nice about the driver is that if you ask it for both a singlet and a triplet calculation, is gonna compute the energy of the approximate singlet using the Yamaguchi spin projection formula that I should have cited here. Yeah, so we've told the driver what sort of excited states we're interested on, and we can ask it to carry out this different sort of calculations in just one input. And why would we be interested in that? Perhaps you're interested in singlet triplet gaps or the annexation potentials or something like this. I am more often than not interested in that. I'm generally looking for the energy of the singlet. But the reason I want to be able to run several calculations at once is because for my final target calculation, which is a singlet, the guess really matters. It makes a whole lot of a difference as to whether you're going to converge your calculation at all, or as to whether you're going to converge it to the right state or not. So for that beta dipeptide system that we were talking about, it turns out that if you feed the closed shell MOs to a ROKS calculation and try to converge it with MOM, you're going to land in the wrong state. In this case, you actually need either the doublet cation or the triplet MOs, I guess. And you can see that convergence is sort of nice and smooth and quick. And, you know, in this particular case, we're talking about a long-range CT state. So that's why the triplets do so well here, because at that point, the electrons are far away from each other, so they don't care about each other too much. So the triplet resembles the singlet. So that's why it's a good guess in this particular case. But it just, in my experience, doublet and triplet MOs are usually pretty good guesses in general. So something nice about the driver is that you can sort of adjust the SCF settings for all these different multiplicity calculations independently. So if you want different algorithms or different convergence thresholds or guesses, you can ask the driver to do this. And what's even nicer is that the driver's smart enough to try to guess what you're trying to do. So that if you say forget a keyword or something like this, it'll try to sort of adjust the SCF settings accordingly to, depending on the state that you're trying to target, to sort of increase the possibilities of you landing on the state that you're interested on. So just briefly, let's walk through what this input in the delta SCF section will do. We're always going to begin with the closed shell MOs, and we're asking for TDDFT state number 5. So we're asking for a singlet, a doublet, and a triplet calculation, all restricted. And the first thing that's going to happen is that the code is going to rotate the canonical orbitals into the NTO basis for the TDDFT state that we're interested on. We are asking that the guess for the doublet calculation be the TDDFT NTOs. So that's going to be fed to the doublet calculation. This is going to be converged with MOM. Notice that we didn't have to tell the driver that. The driver just implied it based on the fact that we're trying to target a high-line excited state. Then we're going to do the triplet calculation, and we're going to be using the doublet as a guess, so we're going to feed it that. And same situation here. You don't need to tell the driver that you want to use MOM. It will guess it based on the state. And finally, we're going to feed that to the singlet, and we're going to converge it with SGM in this case. As I was saying, if you wanted to sort of modify the SCF settings of the different calculations, so if you wanted to use, I don't know, say step for the doublet calculation and then use, I don't know, SGMLS for the triplet, you can do so, but there's going to be sensible defaults in place in case you forget or you just don't want to specify it. Yeah, so we've been talking about TDDFT and TOS as a guess for a few slides now, and maybe let's just talk about that briefly. Why would we want to do that? Well, because it sort of makes sense. Usually, especially when you're dealing with large molecules and when you have augmented basis sets, the TDDFT amplitudes sort of is not just one single amplitude, but there's a number of them. So it's difficult to, or not difficult, but yeah, let's say difficult. It's difficult to single out which orbitals exactly you want to use as a guess for your OO-DFT calculation. In this particular case, for beta dipeptide, there's two amplitudes. Sure, there's one that is dominant, but there's another one that sort of also has large amplitude. So what's nice about the NTO basis is that basically it condenses everything into sort of one, in this case, one single amplitude that encapsulates basically the majority of the excited state itself. So I don't know if I was the first person to think about this. Probably not. I'm certain now I'm not the only one to have thought about this. But I also don't know if anyone else has done anything about this. So now you can run these sort of calculations if you can. Yeah, so we've talked about what we need to tell the driver to run our OO-DFT calculation. Now let's talk about what the driver gives us. Of course, it's going to give us an energy, but energies are not the only thing that you need when you want to compute spectrum. You also need transition dipole moments. And before you could run this, you could get this information in QChem, I think since like 5.4 or maybe earlier, but it was undocumented rem variable. So if you knew, you knew. If you didn't, you didn't. So until I documented it a few releases ago. But with the new driver, you don't even have to think about this. It will just compute the transition dipole like without you asking for it. It doesn't cost anything really. So yeah, this is great. Now you have energies and transition dipole moments that you can then use to compute spectrum. For example, we have the near edge XAS of water once again. And maybe this is a good point to highlight that delta CF is really good. I mean, if you work with core spectroscopy at all, you know that being able to attain this sort of accuracy without any shift whatsoever is completely remarkable. Good point, and once again to highlight that is even better than equation of motion coupled cluster. So with the CVS EOM-CCSD, we don't even match the accuracy that we get with OO-DFT. Side note here, there's different versions of the core valence separation scheme for EOM, which is basically the scheme that we need to be able to target these high-lying excited states. There's sort of the original one that came out in 2015, and a subsequent one that is the frozen core CVS EOM-CC method that came up in 2019. And
You cut out for a second there.
From my point of view, the more the frozen core one under correlates sort of like a cancellation of errors situation that happens. That
sorry, can you repeat that? You cut out for a minute as you were starting to explain the frozen core CVS stuff. So sorry.
Yes. Okay, redo there. No problem. Yeah, redo here. So there's different versions of the CVS scheme, which is something that you need for EOM calculations to be able to target high-lying excitations with equation of motion coupled cluster. And there's different flavors of it. The original or original one came out in 2015, and it carries out an all-electron calculation on the ground state. But the frozen core one, which came out in 2019, it imposes the frozen core approximation on the ground state, and in a sense, it undercorrelates it, and cancellation of error makes it so that it actually matches the experiment better. I believe actually that the more theoretically rigorous one probably needs full triples to beat the accuracy that we're being with OO-DFT. There's a recent benchmark by the Martinez people that came out a few days ago that I think would substantiate this claim. But in any case, this is just sort of a side note, but it's a testament to the fact of how good OO-DFT is for these kind of excitations. In any case, moving on. Yeah, so the Delta SCF driver is also going to give you some useful outputs. One that is super simple, but I think is super crucial, is going to tell you whether you landed on the correct state or not, to a good degree of certainty. So in this case, for example, we're interested in the 1:3 PC transition of water. And this is what the ground state MO looks, the ground state 3 PC orbital. And once you allow the orbitals to relax, in this case, we're using SGM, you can see that the optimized orbital does resemble a 3 PC state. You know, it has the correct nodal pattern, et cetera, et cetera. Well, good, you landed on the right state, no warnings issues. This is sort of what it looks like in the code. It just computes the overlaps, and it tells you if everything's in place or not. And once again, this is simple, but it's super important. And it's super important because often you're not going to land on the correct state, in the one that you are hoping to land on. So if instead of using the SGM algorithm, I use MOM, it turns out that I actually land on a 1:3 PX state. And the driver will practically yell at you through the screen to make sure that you're aware that you've landed on the wrong state. Yeah, so this is simple, but it's important because before there was no way of doing this. Before, or I mean, the way was for you to go and take a look at the orbitals visually to see what state you landed on. And that's okay. Maybe you're just trying to run a single calculation, but if you're trying to run 10 calculations, 20, 100, 50,000, it's a whole different story. You wouldn't be able to visually ensure that you're landing on the correct state. So this warnings and the new driver allow you to do this sort of automatically, so that if you're running a million calculations, you can filter them based on the ones that actually succeeded it or not. And for those calculations that go south, the driver also has a way for you to visualize things. So yeah, say that the code gives you a bunch of warnings and you fear that you've landed in the wrong state. You can ask it to print the cube files of the singly occupied molecular orbitals, so that you can take a look and see which state you landed on. And this is good because I don't know if there's a way to generate, maybe there is ways to generate cube files in QChem for individual orbitals, but well, this makes it easy for you. But if you're trying to deal with F-check files, for example, in this big molecule or big donor-acceptor system that we have here, the F-check file for an augmented double zeta basis is almost half a gig. So you don't want to be trying to open that with IQMO. Yeah. One more sort of measure of how good your calculation is that the driver tells you is how much your excited state orbitals overlap with the ground state. So I personally have not found this to be too much of an issue for delta SCF calculations, but for ROKS calculation, it is a serious issue sometimes. And so let's just go in a brief detour about this. It turns out that the energy and the properties actually themselves of ROKS densities are not invariant to rotations of the open shells. So you can see here, for example, that the energy follows sinusoidal dependence on these orbital degrees of freedom. And so does the overlap with the ground state, and you can actually derive this fairly easily. And yeah, note that this is not the case for delta SCF. So for single determinant theories, high spin situations where everything is pointing in the same direction, everything is invariant. But for ROKS, that is not the case. And this is actually well documented, but I sort of feel it's somewhat forgotten. Like no one told me about this when I was starting to run these calculations, and had to, figure it out by myself, discover it by myself. But yeah, people have known about this for a while, and ultimately, this is related to the fact that you need to define a generalized Fock operator for ROKS. And in sort of the underlying theory, you need to introduce this lambda parameters that for you to satisfy all the variational conditions, they can be whatever, but you just gotta make sure that they're not zero. But the fact that they can be arbitrary means that there's basically different models themselves that can give you different answers. So in the ROKS implementation that we have in QChem, this is how things end up looking like. And in practice, this has consequences. So going back to water, if you're trying to, let's not say minimum, but if we're trying to land on the proper settle point, you'll see that the algorithm actually will incur a little bit of orbital mixing. We're just talking about, a few 1/28ths of a full rotation here, for you to actually find that settle point. And I mean, this is gonna have changes on the order of tenths of EVs, which maybe you don't care about a tenth of an EV when you're talking about hundreds of EVs in the raw energy scale. I cared about it because when I was doing my PhD, I was doing sort of like precision level force spectroscopy. But in any case, in doing so, in trying to find that proper settle point, there's going to be a small amount of non-orthogonality that is going to come into the orbitals as you rotate, as you start to mix those singly occupied molecular orbitals. So maybe you don't care about a few tenths of an EV, but this has really, really big impacts on transition dipole moments. So just even small changes or small degree of mixing can even change the sign of your transition dipole moment. So this gave me a lot of headaches when I was a PhD student, and at some point I was just sitting down, staring at the terminal, and saying to myself, okay, I'm aware that it's this mixing in between the open shells. Why don't we just get rid of it? Zero out the blocks in the Fock matrix that cause that coupling, and see what happens. Yes, we are not satisfying the correct variation conditions because we're setting some of those lambda parameters to zero, which is precisely what Hirao and Nakatsuki told us not to do. But I gotta tell you, it does miracles. It really changes the game, because ROKS convergence for some excited states went from looking like hundreds of SGM cycles to 10, 20, 50 SGM cycles. So convergence really, really improves when you start to suppress the mixing in between the singly occupied molecular orbitals. And not only does convergence improve, I also anecdotally believe that the computed energies and relative transition dipole moments also improve. I think it's clear from this picture on the right here that when you suppress the mixing in between singly occupied molecular orbitals, which is this green curve over here, we're matching experiment a lot better than when we allow it. So I'm actually really curious about some of the other OO-DFT theories that have been coming up. The COOX one that came out recently, I think is really cool because it enforces orthogonality with the ground state directly in the onset. So I'm really curious as to sort of what the topology of the orbital hyperdimensional surface is for this sort of theory. I would assume that maybe it actually improves the situation. And as a matter of fact, quite recently they published a paper in Nature that shows that COOX is actually converges a lot better than delta SCF. And delta SCF doesn't suffer from this issue, but I am curious if sort of the good performance of it has to do with the fact that maybe they don't have to deal with this SOMO mixing. Yeah, so this is sort of the new delta SCF driver, and Once again, I want to highlight that okay, we can use all these different guesses and change the SCF settings and everything, but something that is really simple that really changes the game is just computing these orbital overlaps to make sure that, for example, when you're doing this chain calculations, that you're putting them in place so that you land on the correct state. Once again, this really makes a difference because at this point, this sort of opens up the door for high throughput calculations. You'd have to go and visually take a look at the orbitals to see if everything's okay. So with that said, let's move on to the next part of the talk, which is the work that I've been doing in Sandia National Lab. And once again, this driver came out of necessity because what I'm doing is working with these donor-acceptor systems that feature charge transfer excitations. Why do we care about them? We care about them, us in particular, because we want to design new optoelectronic devices. We want to find materials basically that have large changes in the refractive index when you apply a static field. So that's sort of what we're interested in. But when I was doing the research for this talk, I found it interesting that people were interested in these because of phototherapy, and you can even do synthesis with this. So it seems that they have a variety of different applications. So yeah, I'm just sort of going to walk you through my workflow, through what I'm doing here at Sandia, and show you how this new driver has made a difference. So what I've figured out to do is basically take the core motifs of known donor acceptors and then start to substitute them. So when you go and take a look at this paper, you'll realize that a good number of the acceptors are just sort of aromatics like benzene, naphthalene, and anthracene that have a bunch of different halogens attached in different sort of arrangements and patterns. So the idea is, okay, well, let's just sort of extrapolate this and take the core motifs and start functionalize them with, normal functional groups like carbonyl or OH group or a cyano group or a nitric group or whatever it is. And even with a relatively small number of sort of core motifs, just 21 donors and 8 acceptors, when you start to allow for all these different sort of combinations, you can really, really start to crank up the number of possible donor-acceptor pairs. So the way I've been doing this at the moment is to sort of optimize individually the donor and the acceptor, form a donor-acceptor pair, and then carry out the substitution that you're interested on. And at this point, I'm sort of stuck. I'm not sure whether to re-optimize with DFT or maybe use some of the machine learn interatomic potentials that have been coming out. But in any case, I digress there. But the idea is that once that you have your pair that has been substituted, we then calculate the excited states. And for our particular application, we apply different fields. And out of this comes sort of a lot of useful information. Of course, you get the optimized structure of the core donor acceptor structure. You get SMILE strings, which are necessary for the machine learning people. And the one that I really want to focus on is sort of the excited state calculations. Because what I'm doing at the moment is sort of carrying out the, a TD-DFT calculation. And I use QChem's excited state analysis tools to filter out for states that have that charge transfer state, that charge transfer character that I'm interested on. And I just basically, since I know that it has to migrate from one molecule to the other one, I just look for large distances in the electron hole and the hole. And then I use the new driver that allows me to use that TD-DFT state as a guess, basically, for a subsequent OO-DFT calculation. And me, since I'm interested in singlet states, I'm running ROKS calculations. And since I'm looking for the lower transition, this is the state 1, if you will, I can actually use GDM, which is an excellent solver if you're trying to look for that state in particular. And I don't have to fear about variational collapse in this case because the ROKS unsets itself. It doesn't allow for the closed shell configuration, so it's okay to use GDM. Yeah, so this is wonderful because sort of I can use QChem's excited state analysis to filter out for the states that I'm interested on, and I can use the new delta SCF driver to ensure that ROKS is actually landing on the state that I'm interested on. And this is honestly what allows for high throughput calculations. So the ones that I'm looking at are on the order of 10 to the 5, so hundreds of thousands to even millions of calculations. No, there should be a GIF here with many of the different structures. It doesn't work, unfortunately, but yeah, just high throughput calculations. This would not be possible without the driver because there's no way for me to know if I'm actually landing in the right state. And this is wonderful because it sort of allows us to bring the accuracy of OO-DFT to a large number of large molecules, or what is large for me at the very least. We're talking about 60 heavy atoms almost here. You can see that really does make a difference. The numbers that we're getting here, if we are to trust any of the benchmarks that we were seeing before, are probably even better than equation of motion coupled clusters. So it's really spectacular to be able to carry out these sort of calculations. And well, it seems that that's where the talk ends. So of course, I want to acknowledge the LDRD program at Sandia, which is the one that is funding the work on the DA systems. And I don't work alone, I work with a whole team. And in the theory end, of course, I have to thank Laura. She's my PI here at Sandia. Saket is our machine learning expert. And in the experiment, we have Nick, who helps us with trying to figure out what DA systems make sense and what don't. And Prasad and Christopher, who are the ones that actually synthesize the devices. Thank you to you as well for coming. I'm really happy that people showed up and are excited about this OO-DFT driver. And with that,
oh, there we go. Excellent. Thank you so much for a wonderful talk. I've sorry, go ahead. Oh.
This is where
I'm sorry, you cut out for a second.
Sorry, I'm here. And yes, so presentation is done. I'm happy to take any questions that people might have.
Okay, perfect. Thank you. So the Q&A and the chat should both be open now. So if anyone has any questions, please feel free to post them there. Okay. Well, if no one else has questions, I have one question, which is if you go back to your slide with the gosh, the different definitions of the Fock matrix. This is random curiosity, I guess. But I know so you mentioned that there are a lot of different ways of defining the Fock matrix for restricted open shell systems. Do different choices of definition make any difference in the issues that you see with the lack of what's the best way of phrasing this? The lack of orbital invariance? I don't know if I phrased that properly.
The answer is Uh,
It's fine if you don't have an answer off
I,
the top of
I
your head.
am not sure, but what I can tell you though is that people have indeed sort of looked at different choices for lambda, and there was a paper in 2007 that the reference should be 2008, as a matter of fact, where they were looking at pi to pi star transitions and some small organic systems, and they found that sort of making different choices like lambda equals 2/3 or something like this works better than 1/3. So uh, yes, there is sort of like practical differences that have consequences in convergence when you choose different lambdas. But
Mhm.
I don't know if there's sort of like a proper study as to like what is the best lambda of them all or something like this. And I also don't know if changing the lambda, how that changes the sort of orbital invariant situation.
Okay, awesome. It was just a curiosity, so thank you.
Yeah, for sure.
Um, okay, so we do have a couple questions in the Q&A. The first one
Mhm.
is, so working with the combinatorial bank, did you have to build each one by hand, or were you able to make a script that built that library out?
That's a great question. And the answer is yes, there has been a lot of work that came into this. I can tell you briefly how this looked. The individual donor acceptor core units, which is just sort of 20 donors and 8 acceptors, I build them by hand and optimize them by hand. But then I've sort of built this whole infrastructure that allows you to basically planarize them and make them so that they're lying on the XY plane. Yeah, XY plane. Uh, place them accordingly, and sort of it's a whole thing to build this DA pairs, and this I've built an automated procedure for this. But the initial part, which is just the core motifs, they were optimized in division, like manually by hand.
Okay, thank you. And then we have another question, which is sorry, this orbital optimization is variational, correct? And then if so, what about when DFT may underestimate the excitation energy? That means the optimization would result in a lower energy and therefore a greater error relative to the reference, or from a reference.
Right.
Have you thought of any ways in which you might allow for optimization to a higher energy solution?
Uh, yeah, totally. So, I mean, I suppose these OO-DFT calculations are as variational for the excited states as regular ground state calculations are variational for the ground state, in the sense that DFT is variational so long as you have the exact functional, but we don't. So, in practice, uh, I guess you can say that practical DFT is non-variational in a sense. But so for these OO-DFT calculations, um, you can totally land on different solutions. So you don't only have to sort of you you're not restricted to just the lowest excited state. You can land on higher solutions, and there's specialized solvers for this. So the ones that I was mentioning during the presentation, which I don't know where they are, like MOM, SGM, STEP, all these different solvers, they do allow you to land on higher excited states. So if by variational you're referring to collapsing to the lowest states, yes, you can avoid this, but this is work that a lot of people have been doing in the past few years to be able to access the state that you want, even if it's higher up. Hopefully that addressed the question.
All right. Um, Thank you. Does anyone else have any other questions or follow-up questions? Okay. Well, in that case, I will go ahead and close this up. Thank you again, Juan, for giving an excellent talk. It's the delta SCF and orbital optimized DFT stuff is something that I've been keeping an eye on and tracking for a minute. In because I know a lot of people are getting some good use out of it, and have been for a
Oh yeah,
while. So hopefully the new interface will be something that people find really useful and compelling. And oh, it looks like we do have, oh, we have a thank you for the talk comment as well. So
thank you.
thank you for the excellent talk. If anyone thinks of any follow-up questions that they have, or if you're watching this on our YouTube channel later and have a burning question that you would like to ask, we have a thread on the QChem forum where you can post additional follow-up questions, and we will do our best to answer them. And I guess with that, I will leave everyone to the rest of their day. Thank you again for a wonderful talk, and I hope everyone has a
Thank you for having me.
fantastic rest of your Thursday. So take care, everyone. Bye.
Thank you. Same for you. Bye bye.